Hello, this is Dr. Lewis again. We're just going through some typical problems you might get in an exam question. And the last question, if you look at the past papers from last year on the module which had conjugation in it, has a problem about molecular orbitals. So we're just looking at the pi molecular orbitals because the course is all about conjugation, which is about movement of pi electrons. So it says, draw a molecular orbital energy diagram for the pi orbitals of the compound shown below, and in the MO diagram include the number of electrons in the orbitals and label the HOMO and the LUMO. So you have to show the p orbitals, so not just a case of drawing a few lines, you've got to show the p orbitals. So remember, the first thing is, what is the pi system? So the pi system is just the conjugated system, which is this Allyl system here. So it's just that usual 3 carbon system, which is the one you're interested in. So you're not worried about that or that or that. So it's just the 3 carbon molecular orbital diagram. And there are 3 carbon atoms. That means there are 3 p orbitals contributing to the molecular orbitals. So 3 p orbitals will give 3 molecular orbitals. So the first thing is to do is to just draw 3 carbons in a line like that. So we've got energy going up, and we'll have our electrons filling these orbitals. So we just stick a line in to put the electrons in, and this is the bit we just have to remember. As we go up, we gradually get higher in energy, therefore we get more anti-bonding interactions, we get more nodes. So the first one, the lowest one, is where all the p orbitals are of the same phase, so they're all bonding. There's no, the wave, if you like, goes like that. The next one up has 1 node, and because it's always going to be a symmetrical orbital, the molecular orbital, the node has to be in the middle. So now the 2 ends are of opposite phase, but because the node is in the middle, so if you like, the wave would have gone through there like that. That means that these 2 orbitals where the electrons are sitting in are too far away to be anti-bonding or bonding, so they're simply non-bonding. So they're the same energy as if they're atomic orbitals. And the top one is always a bit like the bottom one, as in it's quite easy because everything is anti-bonding. So it's going to be up, down, up. So the next thing is, you've got the molecular orbital diagram, count the number of electrons. So remember, the anion relates to a lone pair, so that's 2, and the double bond pi electrons is another 2, so that's 4. So there are 4 pi electrons. And so we just fill them up from the bottom like that. So the highest orbital with electrons in it, which is the HOMO, the highest occupied molecular orbital, is going to be this one. And the LUMO, the lowest unoccupied one, is the one immediately above the HOMO, which is that one. That's the empty one immediately above the HOMO. So all you would do for different Allyl systems is, for a cation you just have less electrons, you just have 2 electrons. For one with a radical you just have 3 electrons, so that would be an S HOMO, but the picture of the orbital is always exactly the same. And to be faithful to the question, the question has a methyl there and 2 methyls there, so we can stick a methyl in there and 2 methyls there, 2 methyls there, and that's it.